Welcome back. We have now looked at most of the potential functions which are very much approximated by not only the mathematical formulation, but also there are various formulations and approximations are there, especially with the empirical data that you look at. So, now we go into what is called as first principle, and when we say first principle ab initio calculation and electronic structure methods, that is when we give away most of the approximation, but we come up with a very few approximation and start from the atomic structure of the system. And that is the right way to do. If it was a ideal world, then you would do everything quantum mechanical, and in that case you have to incorporate a lot of these quantum mechanical phenomena which happens around the atoms, the electronic structure, different kinds of atomic variations, and also what we call quantum mechanical wave functions. Because you may have heard about wave particle duality, and in the quantum world everything becomes wave mechanics, and so everything has to have a wave function. And then, as we had seen earlier, by solution of the Schrodinger's equation, you can then calculate these wave of electronic structure and electronic densities, and those electronic densities around the central nucleus has certain location for electrons to exist, and then you have to apply some of the principles of like Pauli's exclusion principle to make sure how many shells are going to be filled up. And also you have to look at some of the other things like the uncertainty principle, where you want to look at the position and the momentum of the particles, and you cannot have both at the same time. So, looking at the quantum mechanical formulation, now we turn to the second generation approach to interatomic interaction, and which is more rigorous approach obviously, but it still keeps the track of Born-Oppenheimer approximation. Let me remind you what we talked about Born-Oppenheimer approximation. That was essentially to make sure that the nucleus of the atom and all the electronic states around that nucleus were all bound to that particular location of the nucleus by adiabatic connectivity. So, what we were saying is that we are going to still look at a nucleus as the central point, and we will approximate all electronic properties around that, and that is still true. However, now we are going to look at the wave function, and that is where this was the method designed by Carr and Parnello. It is one of the seminal papers which really changed the way molecular dynamics simulation is now used in terms of molecular dynamics, as well as in terms of the quantum mechanical effects in the molecular dynamics. So, what we are going to now look at is some of the postulates of density functional theory. Sometimes it is also called density functional approximation, because there are certain approximations that are put into place. For me to be very carefully describe them, let's turn to our slide and read through them, and then I will explain to you what each approximation really means. So, if you look at, it can be shown that the ground state property of the system of interacting electrons depends only on charge density. So, the charge density is very important for the ground state property of a system. So, as you know, in electronic system there are different levels. So, a particle can remain in the ground state, the next step, next step, next step over, and those are integral as well as integers. So, 0, 1, 2, 3, 4, 5. So, if you look at all these states that the electrons can be in, and when they go from lower electronic state to higher energy state, you have to provide some energy to the system, and when they come down to the lower energy state, then they will emit a photon. So, this is how you can excite, and this is where the laser light emission by stimulated emission is created by pumping electrons into higher state. And as they start dropping down, because a lot of them have been put into higher state, they all want to come to the ground state. So, that is where the energy is minimum, and that is the tendency, that is the potential which is available there as you move to the higher state. Similar to if you think about gravity, if you are on a higher plane, then you want to it's easier for you to come down because of gravitational force. So, in this case there is going from one state to another state, and those states are very important here. So, let us look at the charge density, and that was the main contribution of 1964 paper of Hohenberg and Kahn. That has been very famous paper again, and what it means, to find the system energy one needs only to know the charge density. So, the charge density, that is where the density functional approximation comes in, is that all we need to know is charge density distribution, and that charge density is a function of 3 degrees of freedom, as opposed to knowing the wave function which has 3 n degrees of freedom. So, this is where charge density allows you now to approximate a lot of things, because you do not have to deal with 3 n degrees of freedom for every particle, but you can look at the charge density distribution as you go to the electronic system, which is great. Now, if you look at the second postulate, is the ground state energy is a function of which is rho r. So, if you look at density is rho, defined by rho, and r is the position, which is minimized when P r is correct charge density. In other words, there is a variational principle for finding rho r. So, what you are looking at is that you are also finding different kinds of locations and moving the atom, so that you can come to the minimum energy configuration. So, that is where the approximation now goes, is that there is a state of energy which is function of r position, which is minimized. So, what you have to do is you take something particular position and you minimize the energy, and that is what we will look at, how Carpernillo were able to do that very nicely. And the third one, which is again very famous paper, is Kahn and Sham, has derived set of one particle equation to describe the electron ground states. So, we start with the electronic ground state, and so the ground state is defined by the charge density, and it's a charge density we can find and minimize by looking at minimization algorithm for charge density. Once we have the charge density, now we use the Kahn and Sham paper of 1965, and what they say is that you can convert that into one particle equation to describe the electronic ground state. Thus, the interacting n electron problem is mapped exactly onto a one single particle electron problem, and that is very important. Now, you simplified problem while keeping most of the electronic understanding of the atomic structure. Now, finally, the local density approximation, which is the last approximation here, is the exchange correlation energy is given by the exchange correlation energy of a uniform electron gas at the same density. Now, we are also making approximation, a local density approximation, that there is a uniform local density and the same density exists. So, now instead of varying density all over the place, you are able to now come up with different kinds of densities. So, now let me move forward how we do this approach. Unified approach for molecular dynamics and density functional theory can come out of these 4 approximations and 4 postulates. So, let me revise that one more time before we get into the heavy equations. Number 1, we are going to say that the ground state property of the system of interacting electron depends only on the charge density, and for charge density which is rho r, it depends on the position which is the r vector, and you can minimize that to find the ground state energy, which is the correct charge density. So, you have to figure out that, and then the Kahn-Sham postulate says that we can then convert those electron ground state into one particle equations. So, now you do not have to deal with 3 n degrees of equations, and then what we are also approximating, local density approximation, is the exchange correlation energy is given by exchange correlation energy of a uniform electron gas at the same density. And this is where we have to understand that we have made these simplifying approximations, but then the power of this method is that now we are looking at atomic structure or as well as the electronic structure of the material. There is one part is atomic structure, but other one within atom there are lots of electronic structure, and that changes according to the way a molecule is formed or what are the different kinds of shells that are filled in an electron. Thank you.